Hello and welcome. In this video we are going to look at vector fields and the flow of a vector field. So we've dealt quite a bit with vectors, but we haven't dealt with it to the extent that we can populate an entire xy plane with a set of vectors. So a vector field is a plane filled with vectors. For example, we have seen that each point on a three-space surface has a gradient vector which points in the direction of maximal ascent. So if you consider a gradient field and imagining that there was some function f of xy with which we could compute the partial with respect to x and the partial with respect to y to form our gradient vector, which we would write grad f, which equals the partial derivative with respect to x and the partial derivative with respect to y. And at every single point in this plane, we can generate a vector and determine where it points, and we can sketch that vector, and we can do that for infinitely many points inside of the plane. And when we do that, we get an image or a sense of where things move, as if it were a current in a river. So there are different types of vectors that we can have in addition to just the standard gradient vector, and that is a velocity vector. So a vector can represent the velocity of movement. We know that if you compute the magnitude of a velocity, if that vector has components that are in miles per hour, let's say, then the length of the vector itself, using Pythagorean theorem, the units of that will also be miles per hour. And the direction of v tells us the direction of movement. So one example we can consider is the position of a fly in 2 dimensions is given by x equals sine of t, y equals t. Calculate its velocity after t equals 1 second. So the first thing we should note here is that the movement of this particular fly, its x position is changing between -1 and +1, and its y value is simply increasing over time. So if we took a look at this graph, first of all, at time 0, we see that both its x and y positions are 0, so plugging in 0 for t here and here. And then after pi half seconds, x is going to equal 1, and y is going to equal 1 pi halves. So here, if we mark this as pi halves, then our fly is going to be at that position, and then at time pi, the fly is going to be at that position. At time 3 pi halves, at -1, and at time pi, we see that the fly is basically just oscillating back and forth as it's moving upwards along the y-axis. So its position vector, which we often write as r of t, is given by sine t and t. So that means its velocity vector. If I want to know how fast it's traveling in the x direction, all I need to do is compute its derivative in the x direction. I have two position components, so each one of those, when I differentiate with respect to t, that will give me the velocity. So a lot of times we'll call this the v of t vector, and notice we've just taken a derivative of our very first vector. So now if we compute its magnitude at t equals 1, so if I want to know what's the magnitude of the velocity at time 1, all I need to do is take the square root of the component squared, which in this case they're functions. So cosine squared of, did we say 1 back here? At time 1 second. So cosine squared of 1, and then plus 1 squared. And this comes out to about 1.14. So whatever our units of velocity are, feet per second, meters per second, inches per second, whatever it might be, this is the, we could say, units of distance per 1 unit of time. And so that gives us an idea of how we can also work with vectors to establish relationships between position and velocity. Now we could also have force vectors. We've seen these before. The magnitude of the force is the size of the force and the direction it's moving, and the direction of F is the direction of the force. So here we have a couple of examples of vector fields. This one is a vector field of the Gulf Stream. And pretty intuitively, a lot of people will look at this and say, you know, this looks like there's water moving in certain places, almost kind of like little whirlpools, and there's some movement of water over from left to right, and you have another little whirlpool here and another whirlpool here, and there's not really much happening everywhere else where we just sort of see dots or really, really tiny vectors. So that's an example of where we can sort of visualize the flow of a trajectory. Now, whether that point moves like this, if we were to drop, let's say, a feather in there, or perhaps, depending on where exactly we pin it, it might actually start to move in this direction. So we have lots of different things we can visualize from this. The size of the vectors, the length of the vectors, well, if this is velocity, then the length of these vectors is the speed of current, and direction of v is the direction of flow. So if you always think about this in a very intuitive way and think, if I were to drop a feather into this current somewhere, where would it go? Then you get the right idea behind vector fields and how vector fields work. Now we can also have the gravitational field of Earth. Now this is a three-dimensional vector field, and at every single point you see that there's a vector. So at that point there's a vector, at that point there's a vector, at that point there's a vector, and it's really just telling us that that gravitational field pulls towards the Earth. And I apologize if I didn't say that correctly from a physics standpoint, but gravity, right? So we see that there are these force vectors indicating where an object would move if you were to put it within the atmosphere. So we've already kind of mentioned that, oh, and then here we can also say that the magnitude of F is the size of the force, and direction of F is the direction of force. So we've kind of already mentioned a few of these questions here with some talking points. I think we're ready to define what a vector field is. So a vector field in 2 dimensions is a function. It's a function, and it's a vector function. Notice that we have a vector hat over capital F. It takes 2 inputs, respectively the position that you are at in the xy plane. The value at that point is a 2-dimensional vector. So basically we're going to input an ordered pair, and what we're going to get as an output is a vector at that ordered pair. Similarly, a vector field in 3 space is a function of 3 inputs, your position in 3 dimensions, whose values are 3-dimensional vectors. So when we take a look at what we have up here, we see that every single point in this Gulf Stream vector field, at every single point, we can generate a vector. And that vector has, that input requires 2 things. Like, for example, at the point that I just drew, I need the x and the y position, which I may estimate to be about, let's say, 500, 175. That's the position. And then the output, if I put that in to, in this case, my velocity at the point 500, 175, I would get a vector that points to the left and up. And I don't know exactly what that's going to be, but let's say it's about something like negative 2 over 1, or negative 2, 1, excuse me. Let me try that again. We'll say x is negative 1, y is 2. So we'll just pretend that that's that vector right there. So at that point, if I had this function, if I knew what the actual expression was for calculating the vector, then I could argue that by inputting x is 500 and y is 175, the output that I am going to get is this vector, which allows me to plot an arrow at that location. In 3 dimensions, the same idea holds. I just have to input 3 components, my x, my y, and my z, and then what comes out is this vector. So that's all a vector field is. It's a function that just generates vectors, a vector generating function. So let's take a look at an example. Consider the vector field below, f of xy equals 0.5xi plus yj, which can be written in vector form as 0.5x and y. Describe the vector that will be found at each point in the table. What would we expect to see in the graph of the vector field? So if I look at this and I think about how do x and y influence the output vector, I see that the larger the x and the y, the larger this vector will be. I mean, multiplying something by 0.5 will not make it larger, but for very large x, 0.5 of x will be a large number. And similarly, for large y, 1 times y will be a large number as well. And when these are negative, when x and y are both negative, then what I should see is a vector that has 2 negative components. So my guess is the vectors are all going to point away from the origin. But here we have a table of values just to generate some vectors at each of these points. So we said that our vector field is f of xy, vector f of xy equals 0.5x and y. So if I look when x is 1 and y is negative 1, 0.5 of 1 is 0.5 and negative 1 for the y component. So at the point 1, negative 1, which is down here, I'm going to get a vector that points half a unit to the right and 1 unit down. So half a unit to the right, 1 unit down, that vector will point in the direction of this vector here, or this point here. So that is the vector that I can draw at that location. Now, of course, we're not going to draw all these vectors to actual size, because you can imagine as they get longer, they're going to intersect one another. So what often happens in an actual vector field is these get equally scaled down by a factor to make sure that they don't all overlap. Now when x is 1 and y is 0, we get the 0, 0 vector. Half 0, not 1, 0. So taking half of the x value. So at the point 1, 0, I'll have a vector that points half a unit to the right, 0 units up or down. So it points directly away from the origin. At 1, 1, I'll have 0.5, 1. And so that'll be a similar vector as to the one down here. But at 1, 1, I'll have a vector that points is here and points right about to there. And I can do the same thing for these next values. X is 0, so the x component's going to be 0 in all 3 of these. And then the y, negative 1, 0, and 1. So at the point x is 0, y is negative 1, that's this point, I have a vector that points 0 in the x direction and 1 unit down in the y direction. So that's going to be this vector here. And the vector 0, 0, well, that's at the point 0, 0, so there's no force at the origin if these were force vectors. And at the point 0, 1, I have the vector 0, 1. So we see that that's going to be the vector there. And now we can focus on that last row. When x is 1 and y is negative 1, this will be a half and one of these should be negative 1, so we'll make this one negative 1 here. So this will be negative a half and negative 1. This will be 0 and, this will still be negative half, except this will be 0, and this will be negative a half, and this will be 1. So basically these vectors over here are pointing in, are mirror images of these ones over here, but they just point away from the origin. And this one at negative 1, 1 should point to that location, and this one down here should point to that location. And so there's just a sample of our vector field. So if we were to drop a particle in here, we can see that, provided that it doesn't land at the origin, that particle will flow away from the origin. So we have these nice functions called vector fields that allow us to do this. We can also think about those gradient vector fields that we mentioned at the very beginning, where we can have a function that generates vectors in the sense that the gradient vector generates slopes. So the gradient of f at a point a comma b is the partial with respect to x at the point AB and the partial with respect to y at the point AB. And so for every single point, if we compute the gradient vector and calculate its components at every single point AB, then we're going to be able to generate all of these vectors. So here we have a set of gradient fields, and we want to associate it with the contour. So we have to remember that the gradient vectors always point in the direction of maximal steepness. So if I start to look at these, I see that, for example, in this contour plot here, maximal steepness is away from the origin. That is, I always want to move further out away from the origin if I want to have maximal ascent, because I see that as I move outwards, I get to higher and higher contours, so likely something that will look like this. And so moving directly away from the origin will achieve that. So which of these vector fields shows that moving away from the origin will move me in the direction of maximal ascent? Well, this one says moving towards the origin will. This one, depending on which quadrant you're in, it may be the case that moving away from the origin will do that, but I clearly see that these two here go together because these gradients also get longer as we move away from the origin, meaning that there is going to be a higher change in magnitude for the z-value as we move the same distance but farther and farther out. Now in the second one, we see that the contours are getting higher as you move in, so likely what we're seeing is a representation of a upside down paraboloid, and that's clearly this one down here. And here we can see that these sort of say, okay, we move to the next contour by moving in this direction, and we see that that's the case here, that if you move in this direction, you're always going to get to the next contour, which gives us justification for why that's this plot over here. Now, one of the things we want to be able to tell from a vector field is if we were to drop a particle in that vector field, is there a function that models where that particle will go? So suppose we have some vector field, say for the current velocity along some part of a stream. Imagine that a small seed is dropped in at the position x of 0, y of 0 equals 1, 2. Assume the velocity vector field is constant. That is, the velocity has a constant velocity of 3 units in the x direction per unit time and 4 units in the y direction per unit time. And so what that tells us is that if this is in something like meters per second and this is something in meters per second, every second that passes, I will move 4 units further away from the origin in the y direction and 3 units further away from the origin in the x direction. So if this is the velocity vector and I want to know what we would like to represent an actual flow line within the vector field, that is, we want the exact trajectory of the seed. Doing so by eyeballing is tough, right? I mean, it's hard to say exactly where that will stay. Maybe in this case it's a little bit easier because these vectors are all straight and pointing in the same direction. But we want to actually be able to solve this vector field, or solve the flow of this vector field. So earlier we computed the velocity vector from the position vector. Now we have to compute the position vector from the velocity vector. So the position vector is simply going to be the integral of the velocity vector, right? If I know I'm traveling at this speed per unit time, then that means every second that passes, I'm going to commit to 3 more meters. So my position is going to be the integral of 3 dt and the integral of 4 dt. So that will give me, I have to be very careful here. This is going to be 3t plus c, and this is going to be 4t plus c, but it's going to be a different c. So maybe I'm going to put c1 and c2 here to distinguish them. And that should kind of make sense because every second you're achieving 3 more meters. We didn't necessarily start at the origin, so it's not fair to say c1 and c2 are both 0. Because in that case, at time 0, our particle would be at the origin. So we don't want that. We are given some initial conditions here, saying that at time 0, x is at 1, and at time 0, y is at 2. So if I know that my x of t is 3t plus c1, and I'm given that initial condition, I can plug in 1 for x and 0 for t, and I get c1, which comes out to 1. And similarly, my y of t, which is 4t plus c2, if I substitute in my initial condition, 2 for y, 0 for t, and solve for c2, I get c2 equals 2. So that means that my final position is going to be 3t plus 1 and 3t plus 2. This is what we call the general solution. And this is what we call a particular solution because it is particular to the initial condition that we specified. Now we can go over to Desmos and model this to make sure that this seems like it does in fact follow the flow line. So let's go ahead and do that. And here in Desmos, I just put in a slider, and we're plotting the ordered pair 3t plus 1, 4t plus 2. So when t is 0, we see that we're at the point 1, 2. And as time begins to play out, we can see that that particle moves, in fact, along that straight line. We have to zoom out quite a bit because the particle is moving for 10 seconds. So we can see there it goes, and that is how that particle would actually flow. Now it's going backwards. That doesn't match up, but this does. And so that particle will be out away from the origin. Now a notation that we want to get comfortable with is we've already expressed the fact that the velocity vector is the derivative of the position vector. And the velocity vector, if we relate the first and the last thing in this equality here, the velocity vector is part of a vector field, or it comes from a vector field. And so in order for us to calculate the velocity, we need to know the position of that particle. And so the velocity is a function of your position. And that's all we're really saying here. Your velocity vector is a function. Now that function has an arrow over it, right? Because this function is going to output a vector. V is a function of the position. And this is no different than what you've seen before in function notation when we write y is equal to f of x. Now, instead of getting a single output value, now we're going to get a whole vector out by plugging into some function our current position. And another way you could write this is f of your x of t and your y of t. So the flow line of the vector field is the path r of t. It's the actual position, which often involves integration to work backwards. So here's another example. In this case, we have almost parabolic looking flow, so we can kind of see where that particle would go. The one thing to note here is that our function is the vector 1x. So what this tells me is that at any point, the size of the vector, or the vector itself, is going to only depend on the x value that I'm at. The x value itself will always point 1 unit to the right. The y value of that vector will be whatever my x is coming into that function. So for example, if we're at the point 0, 0, if I plug in 0 for x, I'll have the vector 1, 0, which is this vector that we see here pointing to the right. And as we move outwards, let's say to the point 2, 2, well, let's just pretend that's this point here. Well, the x component is going to be 1, which we see there, that's 1. And then the y component will be 2, which is this here. And so then we see that we get that vector. Now, in order to solve this, if this is the velocity, if my velocity vector is equal to 1x, then my position vector, we're going to need to integrate to work backwards, is going to be the integral of 1 dx and the integral of x dy. Here we have to be a little bit careful because x and y are both functions of time. And I made a mistake here. We should be integrating with respect to time here, since we're dealing with velocity. So this should be dt, and this should also be dt. And the challenge that we're going to have with this second integral is that we don't know what x is. X is itself a function of time. So when we write x of t, the x value is in general going to be some component of time, so we can't directly compute this integral because we don't know what x of t equals yet. That is, unless we integrate the top component first. So the integral of 1 is t plus c. And that's perfect because that right there is my x of t function. That is what we're calling x of t. And there really isn't a distinction between using x and x of t. We just write x because it's shorthand, but x itself is a function of time. So now that I know what it is, and I'm going to put a plus c1 here, I am now going to integrate the x function, which is t plus c1, with respect to t. And so the integral of t plus c1 is going to be 1/2 t squared plus c1 times t plus some new arbitrary constant that's going to emerge as a result of that integral. And that is my position function, but I also know that I have my initial condition. So to satisfy my initial condition, I now need to substitute in those values. So at time 0, the particle is at -2, 2. And since I know that x of t is t plus c1, and I substitute in -2 for x and 0 for t, I get a c1 value of -2. Now for equation 2, obviously I can plug in -2 for c1, so y of t is going to be 1/2 t squared minus 2t plus c2. That way I just have one unknown remaining, and I can plug in +2 for y and 0 for t. You can see that we're just going to get c2 equals 2. And so now we have our trajectory for this point. We now know that x of t, y of t, which is just what's inside of our position vector, that's just represents our position vector at time t, is going to equal t plus c1, which is t minus 2, and 1/2 t squared minus 2t plus 2 for the y component. So let's model that in Desmos. So here we are. I have those two functions in, and we just see that we can verify that at time 0, the point is at -2, 2. If I press play, I can see that particle moving parabolically, and you can actually see it speeding up in at least the y direction as time passes. You can see it's going faster and faster in the y direction. Well, that's because we have a 1/2 t squared in there. So as t gets bigger, t squared is going to get bigger, which is going to make that y component grow really fast. Okay, one more example, and this one is can be a little bit tricky because we first of all see that the vector field is circular in motion. So that's kind of the key hint here. But our velocity vector, v of t, is equal to -y for the x component and x for the y component. Now this is totally normal. There's nothing wrong with the x component, the velocities being mixed, that they may depend on both the x and the y. So we're just saying that this is the derivative of your x position is -y. The derivative of your y position is positive x. So this is actually what we call a system of differential equations. And right now we don't really know how to solve this because, once again, we would just say that your position is going to equal the integral of your x prime with respect to t, and your y component is going to equal the integral of y prime of t with respect to t. And the problem is we can't really compute these because y and x are both some unknown functions of time, so we cannot integrate them with respect to t. because y depends on t, as does x. However, if we look carefully at this, if we're saying that the derivative of some function equals the negative of y, and the derivative of y equals exactly x, that tells me something about how x and y are related. That is, when I take the derivative of x, I get the opposite of y. And when I take the derivative of y, I get x. So that's kind of weird. If you think about what kinds of functions these can be, well, what if I had just guessed something like t squared? Well, the derivative of t squared is 2t, but the restriction must be that that equals the negative of y. So in that case, y would have to equal negative 2t, because x prime of t equals the opposite of that. But then my y prime of t here would be equal to negative 2, and by this statement, the derivative of y has to equal x, but I clearly see that those two things don't equal each other. So I do know of a function that will cause one function to be the other function's derivative and vice versa, and that is, well, when I use sine and cosine. For example, if x of t and y of t, if y of t is equal to sine t and x of t is equal to cosine of t, I can check to see that the x prime of t is equal to negative sine of t. And I see that x prime is the opposite of y. Y is sine of t, x prime is the opposite of that. So that's a check. That works out. That's exactly what we were intending to find. And similarly, if I take the derivative of what I claim to be y, which is sine of t, I get cosine of t, and y prime of t is equal to x, in fact. So we see that those two are equal to each other. And so in this case, our solution, and really this should be plus c1 and plus c2, our position function is equal to our x of t, cosine t plus c1, and our y of t, sine of t plus c2. Now, the initial condition that I get will determine whether I'm traveling along this ring, or say this ring, or this ring, or this ring, or rings that are further out. That will be dictated by the initial position that we choose. And that's dealing with the flow of a vector field. Next, in the next lesson, what we'll get into is the idea of a line integral, which says you can go with the flow, but a lot of times, like when you're dealing with magnetic fields, things cut across force vectors and go in directions maybe against the vector field. So the question that we might have now is, well, what if I want to go that way? What would that require of me? And that's what we'll get into next.